Okay, let's unpack this. For the last few years, we've all been pretty obsessed with what large language models can do.
Absolutely.
Their creativity, the speed, the code generation, it can feel like actual magic, but
Yeah.
there's always been this flaw, right? This really frustrating fundamental problem that holds them back from truly evolving.
Catastrophic forgetting.
Catastrophic forgetting.
So it
Yeah.
really is the Achilles heel of modern machine learning.
Mm.
You train these incredible systems, these billion parameter models, on just vast amounts of data.
Right, they become these general geniuses.
They do.
Yeah.
But the second you try to fine-tune them on a new task, say you want to make it an expert in medical coding, it essentially just overwrites its core knowledge.
It sacrifices the old stuff to learn the new.
Exactly. It sacrifices that proficiency on all those foundational tasks.
Yeah, it's like cramming for a huge exam and then, on the morning of the test, you've suddenly forgotten how to drive your car.
That's a great way to put it.
It's AI amnesia. And it means every time we want an LLM to adapt, we either have to go back to square one or spend a fortune on partial retraining.
And if you need a sort of clinical analogy to hold on to, it's very much like anterograde amnesia in humans.
The inability to form new long-term memories.
Precisely. Current LLMs are, by their very design, confined. They're stuck with their immediate working memory, the prompt you just typed in, or the static information from their initial, very expensive pre-training. They just don't have that organic way to accumulate new wisdom over time without destabilizing the old.
Which brings us to our mission for this deep dive. We're looking at what could be the definitive answer to this coming out of Google Research in their new NeurIPS 2025 paper. They're calling this new approach nested learning, or NL, and it promises to solve this AI amnesia by completely changing how we even think about AI architecture.
This isn't just another algorithmic tweak.
No, this is a new foundation, one that's designed from the ground up for lifelong learning. So when you look at how researchers have tried to fight catastrophic forgetting in the past, they usually fell into one of two camps, right?
Yeah, that's right. You had, on one hand, the architecture people. They were trying to add protective layers or maybe freeze certain parameters to protect them.
Okay, the structural approach.
Right. And then you had the other camp, the optimization folks, who were focused on the training rules. They were trying to make the process slower, more selective, maybe using different kinds of loss functions.
They were separate efforts.
Entirely separate. They were trying to bolt solutions onto what was, fundamentally, a broken framework. And the key limitation there was that for decades, the model's architecture, the actual network structure, and the optimization algorithm, the training rule that dictates how weights are updated, they've been treated as two completely separate concepts.
Why does that separation matter so much? I mean, intuitively, it sounds right. The blueprint of a house and the process of building it are different things.
It sounds right, but it prevents the model from doing something crucial, learning how to learn over time.
Ah.
To connect this back to biology, the human brain is the gold standard here. It adapts through neuroplasticity. The actual structure changes in response to experience.
So the structure and the process are the learning. They're intertwined.
They are one and the same. And current LLMs, because of this artificial separation, they just lack that ability to update their knowledge across multiple timescales. And that is what human learning is all about. It's the difference between memorizing a flashcard and actually gaining wisdom.
And that's the philosophical gap that nested learning is trying to bridge. The paper introduces this idea by viewing a single ML model not as one continuous process, but as a system of interconnected sort of multi-level learning problems.
That are all being optimized simultaneously.
Right. It's like having mini models inside the main model, all focused on different time horizons.
What's fascinating here is just how deep that philosophical shift goes. Nested learning basically argues that a model's architecture and its training rules, the optimization algorithm, are fundamentally the same thing.
Okay, hold on.
They're just different levels of optimization happening in parallel. Realizing that gives you a completely new dimension for designing these AI systems. You're no longer just training weights, you are training the rules that train the weights.
So it's a feedback loop. The structure dictates the rule, and the rule then modifies the structure.
You got it.
I can see why that's a paradigm shift, but how does that actually work mechanically? I mean, what are the practical levers they're pulling to make this happen?
They focus on two key levers here. The first one is what they call context flow.
Okay.
In a nested system, each of these internal optimization problems gets its own distinct flow of information to learn from. So instead of one massive fire hose of data hitting everything at once, you get these localized currents.
So a low-level problem only sees data relevant to its specific job.
Precisely.
Okay.
It keeps the signals clean, while the high-level problems, they get to see the consolidated results from below. It's just good management, as you said.
Okay, that makes sense. And the second concept, I'm guessing this one has to deal directly with the forgetting problem?
It does. The second lever is multi-timescale updates. This is how we solve the amnesia problem. We define an update frequency rate for each component.
How often it gets to learn something new.
Exactly. And by setting different frequencies, you can order all these interconnected problems into specific levels that run at different speeds. The fast levels handle the immediate, in-the-moment learning. The slow levels handle the deep foundational knowledge consolidation.
So you have this ordered set of problems, all running at different speeds, all at the same time.
That is the heart of the nested learning paradigm.
So let's try to ground this a little. How does this apply to the parts of a transformer that we already, kind of understand?
That's a great question. The researchers illustrate the concept by modeling the whole learning process through the lens of associative memory.
The ability to connect one thing to another.
Right, mapping and recalling. They show that the training process itself, specifically the famous backpropagation algorithm, can be modeled directly as an associative memory module.
Wait, okay, hold on. Backpropagation is just the math we use to send the error signal back through the network to update the weights. How is that associative memory?
Well, think about what it's doing. Backpropagation is mapping a given data point to the value of its local error.
Okay.
And that error is really just a measure of how surprising or unexpected that data point was, given where the model is at.
So in this framework, the model is associating the input with the correction it needs.
Yes, it's a memory recall process
Yeah.
where the correction is retrieved based on the input.
Ah, okay. The error signal isn't just a number. It's a memory of what the model got wrong.
You've got it. And they extend this view to the architecture itself. Components we all know, like the attention mechanism in transformers, can also be formalized as a simple associative memory module, one that learns the mapping between different tokens in a sentence.
And when you see everything as a coherent, reusable memory structure,
Then you can apply these multi-timescale updates consistently across the entire system. It all clicks into place.
this philosophical unification is clearly powerful. And the source material highlights that this leads directly to two very practical, immediate applications that demonstrate its power. Let's start with deep optimizers. We know optimizers manage the training process. How does NL change standard optimizers like the ones handling momentum?
The limitation the NL team identified is that many standard optimizers rely almost exclusively on a very simple metric, dot product similarity.
Which, for you listening, is a very basic way of measuring how alike two vectors are. It's simple pattern matching.
It is. And it works fine for general training, but it isn't very robust. It doesn't really account for the complex relationships between different bits of data, which makes the whole optimization process vulnerable to noisy or imperfect data.
So if I give it a batch of data, the optimizer is just looking for things that look similar to what it just processed instead of looking for deeper patterns?
That's a perfect way to put it. And nested learning addresses this by changing the underlying mathematical objective of the optimizer itself.
It changes its goal.
Exactly. Instead of relying on dot product similarity, they switch to a more standard, robust metric, like L2 regression loss, as the internal objective. By optimizing the optimizer to minimize a proper loss metric, rather than just matching simple similarity, they derive new, smarter formulations for core concepts like momentum.
That's a huge shift. You're essentially optimizing the learning rule to be more resilient to imperfect data, creating a better learning process from the inside out without increasing the training time. That's efficiency and intelligence rolled into one.
And this leads us directly to the second major application, the Continual Memory System, or CMS. If we look at a standard transformer architecture today, we have that binary split.
Right, the two boxes.
The sequence model, so the attention layers, that acts as your short-term memory. It holds the immediate context. And then you have the feed-forward networks, which act as the long-term memory, storing the pre-trained knowledge.
Short-term versus long-term. Seems simple enough. How does CMS improve on that?
NL just throws that binary split out the window. It extends it into a true continuum. The continuum memory system sees memory not as two boxes, but as this vast spectrum of modules.
So instead of just short and long, you have dozens of levels.
Potentially, yeah.
Mm-hmm.
Each updating at a different, specific, mathematically defined frequency rate.
That seems incredibly complex to manage. What's the benefit of having all that granularity?
The benefit is decoupling. Your very fast layers can adapt instantly to the current context. Say, adapting to your specific speaking style during this one conversation.
Okay.
Meanwhile, the mid-speed layers might update on a daily basis, and the really slow layers are responsible for consolidating that core pre-trained knowledge over weeks or months. And this is absolutely critical. It prevents the new information, the high-frequency updates, from catastrophically destabilizing the deep foundational knowledge held in the low-frequency layers,
It allows for graceful, continual integration.
which is exactly what human learning achieves.
So this CMS system and the deep optimizers are the practical outcomes of this nested learning theory. And to prove it all works, the researchers built a proof of concept architecture. It's called HOPE.
That's right. Hierarchically optimized persistent experts.
I like the name.
That's a good one. HOPE is a self-modifying recurrent architecture. So it processes information sequentially, and it's built from the ground up using these NL principles and the CMS blocks. It's also worth noting it's a variant of an established model, the Titans architecture, which was already a strong contender. But HOPE is fundamentally different.
Because of the nested design, so what unique capability does HOPE have because of this structure? Is it just faster, or is it genuinely smarter?
It's smarter because of how it learns. HOPE takes advantage of what they call unbounded levels of in-context learning.
Unbounded levels.
Because of that nested structure, the model isn't just learning the task. The nested optimizers inside it are simultaneously learning how to adjust the learning parameters for the architecture above them.
It's optimizing its own memory.
Through a self-referential process, it creates an architecture with, in theory, infinite looped learning levels. It's a truly self-improving system.
That is the ultimate goal, isn't it? A model that learns how to learn better over time without a human stepping in to tweak the optimization rules.
It is.
So how did it actually do? How did it perform against the current state of the art?
The experimental results gave a very clear validation of the theory. On standard language modeling and common sense reasoning tasks, HOPE just showed superior performance. Specifically, lower perplexity and higher accuracy compared to other modern recurrent models like Titans and Samba, and also standard transformers.
Perplexity is a term we hear all the time. For you listening, why does lower perplexity matter so much?
Perplexity is essentially a measure of how surprised or, confused a model is when it's predicting the next word in a sequence.
So lower perplexity means it's more confident.
More confident and more accurate in its predictions. The fact that HOPE was consistently less perplexed shows that its internal model of the world is more stable and coherent.
And crucially, how did that continuum memory system hold up under stress?
That's where it really shined. They tested HOPE on really difficult long context tasks, specifically the famous needle and haystack tests, the NIAH tasks.
Okay, let's quickly define that. What is NIAH and why is it considered the gold standard for testing long context memory?
It's exactly what it sounds like. You take a single critical piece of information, the needle, and you embed it deep inside a massive document, the haystack, sometimes tens of thousands of tokens long.
And the model just has to find it.
It has to accurately recall or use that one fact. Success in NIAH, especially in the harder variants, proves that a model can retain key details over these huge extended sequences without forgetting them halfway through.
And HOPE's CMS blocks.
They absolutely dominated these tests. HOPE showed superior memory management, higher retrieval accuracy. It proved that the continuum memory system is a fundamentally more efficient and effective way to handle long context than what we're using now.
Architectures that just kind of degrade the longer the input gets.
Right. The decoupling of the memory rates, it works.
So what does this all mean for us? We started this conversation with catastrophic forgetting, this huge bottleneck that has crippled the idea of a truly self-evolving AI. Nested learning isn't a patch. It feels like a robust foundational shift. It seems to close the gap between the limited LLMs we have now and the incredible continual learning ability of something like the human brain.
I think that's the right takeaway.
Yeah.
And the professional implication here for every engineer, every company using AI, is that this enables a real shift away from these rigid, expensive to retrain models.
Towards what?
Towards adaptive, lifelong AI agents. Models that can continually personalize themselves, that can integrate real-time data, new research, market changes, without the catastrophic computational hit of erasing their past.
That's the next critical step.
It might be the inevitable step towards robust, truly generalizable AI that can organically grow and evolve over its entire operational lifetime.
It is staggering to think that we may have unlocked a whole new dimension for AI design just by unifying architecture and optimization, by letting the system figure out its own best learning rules. Which leaves me with one final thought. If AI can learn how to learn better by adjusting its own internal rules, what does this imply for the future timeline of technological growth, and how might that accelerate development in fields where knowledge accumulation is absolutely critical, like general science or health and bioscience?